Welcome to The Explainer. Today, we're going under the hood, deep into the engine room of Bitcoin. We're going to follow one single transaction from the very beginning all the way to the end when it's basically set in digital stone. It's a fascinating process, so let's get into it.
All right, so before we get too technical, let's just step back and think about the big problem Bitcoin was trying to solve. You know, in the real world, if I give you a $10 bill, that's it. It's yours. I can't spend it again. But with digital stuff, anything can be copied, right? A file, a photo, anything. So how in the world do you stop someone from just copy-pasting their digital money and spending it over and over again?
That's the million-dollar question, and it's called the double spend problem. It's the Achilles heel of any digital cash system. Satoshi Nakamoto's white paper was all about cracking this nut, but doing it without a middleman. No bank, no PayPal, nobody in the middle to give the okay. So how do they pull it off? Well, to see how, let's follow the money.
Okay, to really understand how Bitcoin solves this, we're going to follow the complete journey of a single transaction. Let's imagine a user, we'll call her Monica, is buying a car and needs to send 0.9 Bitcoin to the seller.
So the very first thing you need to get your head around is that a Bitcoin wallet isn't like your bank account. There isn't just one big balance. Nope, it's way more like a real, physical wallet full of cash. It's got a collection of digital bills and coins, and these are called unspent transaction outputs, or UTXOs for short. Just think of them as individual pieces of digital cash.
And here's how those digital coins work. To make our 0.9 Bitcoin payment, Monica has to use a UTXO she already has. Let's say she has one worth 1.1 BTC. Now, she can't just tear off a piece of it. Just like with real cash, you have to spend the whole bill. So the entire 1.1 BTC UTXO gets consumed, and in its place, the transaction creates two brand new ones. 0.9 BTC goes to the car vendor, and the other 0.2 BTC comes right back to Monica as her change.
So, how does she prove she owns that 1.1 Bitcoin? This is where the magic of cryptography comes in. She has two keys. Her public key is kind of like her bank account number, totally safe to share with anyone who wants to send her money. But her private key, that's the secret sauce. It's like her password, and she uses it to create a digital signature that authorizes this one specific payment. It's mathematical proof that she, and only she, has the right to spend those funds.
Now, holding all this together is something called Bitcoin script. And honestly, it's a surprisingly simple, you might even say primitive, programming language. You're not going to build the next big app with this thing. It has one job and one job only: to act as the rules for a digital lockbox. It defines exactly what conditions have to be met before a UTXO can be spent.
And here's the absolute genius of it. It's just powerful enough to do cool things, like requiring, say, 3 out of 5 people to sign off on a transaction. But it's also intentionally limited. For example, you can't create loops in the code. And that's a feature, not a bug. It makes it impossible for a transaction to get stuck running forever and gumming up the works for the whole network. Its simplicity is its greatest strength.
All right, so Monica has built her transaction, she signed it with her private key, it's all ready to go. So, now what? Where does this thing actually go?
Well, it doesn't go to some central server at Bitcoin headquarters. Instead, her wallet just broadcasts it out to a few of the other computers, we call them nodes, that it's connected to on the Bitcoin network.
And from there, the transaction spreads like wildfire. It's literally called a gossip protocol. Every computer that receives it checks to make sure it's valid and then passes it on to all its friends. Within seconds, Monica's transaction is sitting in this digital waiting room called the mempool on thousands of computers all around the world, just waiting to get picked up.
And this is where things get really, really interesting. For Monica the payment to be final, it needs to be included in a block and added to the permanent public ledger. And there is a massive global competition happening 24/7 for the right to do exactly that.
This competition is called mining, and it is the very heartbeat of Bitcoin security. It's this incredible system that allows thousands of total strangers to agree on the state of the ledger, without any boss telling them what to do. The whole system is called proof of work, and it basically forces these miners to burn real-world electricity to solve an incredibly hard math puzzle. The prize? The right to add the next page to the history books.
This one sentence nails the essence of proof of work. The whole trick is that finding the answer to the puzzle is unbelievably difficult. But once someone finds it, it's super easy for everybody else to look at it and go, yep, that's the right answer.
So what is this puzzle they're trying to solve? Well,
A miner grabs a whole bunch of pending transactions from the mempool, including Monica's, and bundles them together. Then, they have to find one specific magic number, called a nonce. You can think of a hash function like a digital blender. You throw in all the transaction data, you add your guess for the nonce, you hit blend, and out pops a totally unique code. The goal is to find a nonce that makes that final code start with a whole bunch of zeros.
The thing is, there's no shortcut. You can't predict which nonce will work. The only way to find it is pure brute force guesswork. You try a number, hash it, check the result. Nope. Try another one, hash it, check it, nope, over and over. It's basically a giant digital lottery, and miners are buying billions of tickets every single second.
And the scale here is just mind-boggling. To give you some perspective, a single mining machine can check billions of these nonces in just a few seconds. Now, picture thousands of warehouses filled with these specialized computers all around the world, all guessing at the same time. This incredible amount of energy being spent, that is the work in proof of work. It's what builds the digital fortress that protects the blockchain. And then it happens. After trillions and trillions of guesses, one miner, somewhere on the planet, finds a winning nonce. They've hit the jackpot. So what's next? How does this make Monica's payment official?
The winning miner instantly shouts their solution to the whole network. And remember how we said verification is easy? Well, every other computer immediately checks the work. They see the hash is correct, they see all the transactions inside are valid, and they add this new block to their own copy of the chain. And boom! Just like that, the entire network reaches consensus. Monica's transaction is now officially confirmed.
And that's pretty much the end of the line. The process is complete. Monica's payment is now cemented into this global, shared, and most importantly, unchangeable record book. The double spend problem is solved. That original 1.1 BTC UTXO she started with is gone forever, and the car vendor knows with 100% certainty that they've been paid.
So, what makes it so permanent? It's the chain part of blockchain. You see, each new block doesn't just contain transactions. It also contains the unique digital fingerprint, that hash, of the block that came right before it. This creates an unbreakable, cryptographically linked chain. If a hacker wanted to go back and change Monica's transaction, they'd have to redo all that mining work for her block and for every single block that came after it, all while racing against the entire global network. It is, for all practical purposes, impossible.
And that's the journey. It's this beautiful, intricate dance of cryptography, raw economic competition, and decentralized agreement. What you're left with is a system that creates trust between strangers, with no need for a powerful company or government to play referee. It really makes you think, doesn't it? If we can solve the problem of digital money this way, what other industries could this kind of thinking completely transform? Thanks for watching.